Welcome to Code Quality. Today we'll be taking a look at question 572 in LeetCode, the subtree of another tree problem. And so the question is, you're given two trees, in this case S and T. Can you determine if T is a subtree of S? So let's start out with the definition of a subtree. A subtree is any node plus its children combined. So in the case of S, we have 5 subtrees. The first one is 3 plus all of its children, so that would be the entire tree. The second one would be 4 plus its children. 1 and 2 are also subtrees. And 5 would also be a subtree. So the question here is, T, which is 412, is that a subtree in S? Indeed it is. As you can see, we have a 412 here, and we also have a 412 here. Next, let's move on to the code. We're given the following method signature, this subtree, which takes two tree nodes, S and T, and returns Boolean. A tree node is simply a class that contains a value, an integer value, and a reference to a left tree node and a right tree node. Obviously, if left is null, then we have no more children on the left side of the current node, and if right is null, then we have no children on the right side of the current node. We're going to solve this problem by first writing an algorithm to determine whether two trees are equal or not. Once we have an algorithm for checking whether two trees are equal or not, we're going to iterate through all the nodes of S, since each node in S represents the root of a different subtree. Then we check whether T is equal to the selected node in S. So down here I have the method signature for our function that's going to determine whether two trees are equal or not. As you can see, it takes two tree nodes, S and T, and returns a Boolean. True would mean both trees are equal, false would mean the trees don't match. The first step to determine whether two trees are equal or not is to first check whether the roots are equal. To do that, we write an if statement and we check if s.val is equal to t.val. If they are equal, then we need to make sure that the left subtrees of S and T match up and the right subtrees also match up as well. We do that recursively. So return trees are equal of S dot left and T dot left, and right, so we need the left side and the right side to both be equal. So trees are equal of S dot right and T dot right. Let's go ahead and move on to the base cases. Basically when we don't have any recursion and return either true or false. Our first base case is when s.val is not equal to t.val. So if s.val is not equal to t.val, then we return false, since the two trees can't be equal in such a situation. In addition, since we have this if statement now, we don't really need to check if s.val is equal to t.val. Well, they must be equal. Our next base case is if S is equal to null and T is equal to null. In such a situation, we know that everything that we've checked so far, either from the left side or the right side, must be true. So in such a case, we return true. Just keep in mind this doesn't necessarily mean the two trees are equal. It just means that everything we've checked so far is true. And our final base case is if S is equal to null and or T is equal to null. What this is saying is we have no more children for either S or T. But one of them must have children, since our first if statement checked if neither had children. Right, so in this case we have either S or T not having a child, which obviously means they're not equal since one tree node has a child but the other doesn't, so in such a case we return false. And that's it. We have our algorithm to determine whether two trees are equal or not. Just to recap, our strategy to solving this problem is by iterating through all the nodes in S and comparing that node to T, since essentially each node in S is representing a subtree rooted at that specific node. So let's move on to the solution. We begin by checking whether the two trees rooted at S and T are equal or not. If they are equal, then we return true and we're done. If they're not equal, then we check recursively is subtree of s.left and T. Similarly, we do the same with the right side of S. This works because s.left represents the root node of the left subtree of S. Similarly, s.right represents the root node of the right subtree in S. Of course, if we never find two trees that are equal, then we just keep on going left, 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 or right, right, right. And at some point, we need to stop the iteration. So we check if S is null. If it is, then we have no more children or nodes to compare to T, and we simply return false. And that's it. That's our solution to the subtree problem. Just to recap, we have a trees are equal method, which determines whether two trees are equal or not. And then we simply iterate through all the nodes in S, since each node in S represents the root of a different subtree in S. So we check if the two nodes given, S and T, are equal. If not, then we recursively iterate through the left and right subtrees in S. So that's it for this problem. So for space complexity, I want you to notice that in the worst case, the maximum height of a tree would be the number of nodes in the tree. So for example, in this tree we have 3 nodes and the height is 2. But in the worst case, let's say for example all nodes were on the left side of 4, then the height would be 3. So our worst case space complexity would be big O of the number of nodes in our tree, and in this case we assume that S has more nodes than T, so the space complexity would be big O number of nodes in S. For the time complexity, we iterate through every node in S, 3, 4, 5, 1, 2, and for each node we compare it to T. So on average, we could say we have the number of nodes in S multiplied by the number of nodes in T. So if we have, let's say, 5 nodes in S and 3 nodes in T, then on average we're performing 3 times 5 comparisons. Thanks for watching, and if you have any questions, please don't hesitate to leave a comment below.